pretend we're just doing a full technology refresh. Say we're
Hmm.
starting from scratch. Maybe you're spinning up a startup with an Infineon
Hmm.
to develop a new, maybe it's a new technology node or something like that. What are the sorts of technological challenges you're going to face, and what sorts of techniques and teams will you need to build to overcome them?
Yeah, I mean, if you're getting into a completely new space, you can break it into a little bit of compartments, right? One, you're going to need to have the process technology, say either in your fab or somebody else's. So there's a technology development aspect. So like, does that technology exist either in your company or externally? If not, now you got to go develop it. So that's just core R&D of process technology, call it in silicon or some other exotic material. Then you need your design team. So you got a whole set of engineers for that. You're going to need your packaging engineers. And by the way, the design people can be analog, they can be mixed signal, they can be digital. There's a lot of compartments, you got to fill. You got your packaging expertise, you got your test engineering expertise, you have your whole operations flow. So, to bring a new chip from, say, a startup out to the market, there's a lot of compartments you got to check off to get there from beginning to end, right? So it's not a small endeavor, and generally, it's going to take a lot of investment, and it's also going to take a lot of partnerships, right? It's going to take people working together. There's outside firms that can help, but it's not generally going to be from one entity, all on their own.
You can't vibe code your way into having a new ASIC.
No, no, it takes an army.
So this new radar chip you've developed is 60 gigahertz, millimeter wave. Who? Let's start with why. Why go up to these, super high frequencies?
So, I mean, there's 24 gigahertz radar chips in the market. I mean, we've had those previously even in our company, and there's others out there in the market. And then there's also 77 gigahertz in the automotive space. That's a very special use case, 77 gigahertz for automotive. It's a band that's been reserved for automotive, and it's largely due for regulation and safety reasons to keep others out of that band, and it's only for that because automobiles are using that frequency. So if we kind of put that aside for a second and we say, why 24 versus 60? So with 60 gigahertz, as you're operating at a higher frequency, you're going to get much more resolution on with the measurement and more accuracy in your presence detection. So you get some unique benefits of moving to higher frequencies. The other thing that's notable is that when you go to higher frequencies, the antennas get smaller. So as the antennas get smaller, now you can start to do things like we have done where we bring the antennas into the package. So now we can bring, a fully integrated radar chip with the antennas, and now your end customer doesn't have to do antenna design on their PCB or somewhere else in their system, and now they can use standard FR4 materials. So there's a lot of inherent benefits to go to 60. You can do sub-millimeter accuracy, you shrink the device, sensitivity, range, a variety of things.
So I'm curious about the antenna integration. Are you just basically like sputtering onto the chip and you have your geometry and that's how it works? Or how do you actually go about building an antenna knowing it's going to be inside of an IC package?
It's actually fabricated into the packaging of the device. So it's not actually on die.
I've said it before, I'll say it again. Packaging engineers are kind of the unsung heroes of the space, and the innovations they have makes everything else possible. What sort of unique challenges do you come across when you're trying to do this type of integration inside of a package?
Yeah, I mean, it gets pretty complex, especially if you think about you have multiple die and how do you stack die? How do you isolate the die? How do you wire bond to them? How many layers are going to be in your package and shelves to wire to then route everything to your board? You're right. They're the unsung heroes, I would say. At the end of the day, you can have the perfect piece of silicon that works great, but if it doesn't work in the package, then you don't really have a product. One thing about, going back to MEMS is that in MEMS, you're typically measuring, say, motion or position or maybe stress, as we talk about the pressure sensor. Well, if you don't design your package correctly to, say, mitigate stress, you're going to measure the unintended stresses of your PCB over temperature and flexing. So, you're going to be picking up measurements you didn't want, right? So that packaging is so important, especially when it comes to MEMS, that you don't really see in standard silicon issues, right? It becomes much more pronounced in MEMS devices.
Yeah, it sounds tricky. Um,
Yeah.
how do thermals play in? Does the antenna impact thermal performance or anything like that, or is that less of a concern here?
Less of a concern. I mean, we qualify our devices up to, industry standard temperatures. We design for different temperatures and the effects on the package and stresses. Yeah, we account for all that.
And the idea of going 60 gigahertz is that it doesn't have to be an automotive radar specific chip. It has the band that it can kind of do other sorts of applications. Who do you think will be incorporating this sort of sensor into their systems?
Let's go back to automotive for a second. It could go into in-cabin automotive. The 77 gigahertz is really for the outward-facing, autonomous vehicle type stuff. So it can go into in-cabin. But largely where we see a lot of traction with this device is, say, in consumer devices and IoT applications. And so if we drill down a little bit there, security cameras and video doorbells where you say want to wake on motion. Radar gives you a lot of hooks to configure the device for different ranges, field of view, so you can actually zero in on where you want to measure so you get less false positives so you're not waking up that camera constantly because some of those are battery powered, right? So you're going to consume power there. Very similar application would be smart thermostats, where you want to detect presence in the home, turn on the display. You may have pets in the house that you want to discriminate against and not count them, so they're not turning on your HVAC system automatically. Smart TVs, smart speakers, say you want to know there's people in the room. You may want to count the people. You may want to know where in the room they are, so you can take other action as far as how you change acoustics. You can even do gesture sensing with radar. And then it's similar application to that is kind of HVAC systems where again, you want to detect people. You want to know maybe how many people are there, where they are in the room. Gestures again, you can do other things. And then we get into a little bit more other areas like computing, like so laptops, computer vision, or computer monitors, let's say. If I'm in front of my monitor, I want it to turn on. When I leave, I want it to turn off. I can save power that way. I could tell if there's a user behind me because now you're counting again, so you can tell there's people behind you. Hey, you got somebody behind you. What are you looking at? Be careful. And then, there's a slew of home health applications as well. If you think about what I mentioned on 60 gigahertz radar, how it can do, it can do down to sub-millimeter accuracy. So you can actually get into vitals. So you can detect breathing and heart rates of users, fall detection of somebody in a room. And there's a slew of, call it home health applications where radar could be used.
What does the kind of transmitter receiver setup look like for this? Is it a bunch of TX/RX kind of wedged out? Like, obviously, you don't have a laser spinning like a LiDAR system. What does that configuration look like?
Yeah, so I mean, we make a variety of radars. So we generally bring out a one transmit, three receive. And the reason for that is, on the receive side, you now can detect and do measurements of motion. So we basically collect velocity, angle, and Doppler, right? So with different configurations, you can collect for different use cases, right? So like that's what we call a one transmit three receive. We have a 2 and 2. You can do 2 and 4. There's a lot of configurations depending on the use case, the size you can work with, and they get more complex obviously as you have more data.
I never thought about Doppler in this application. I think about it for, speed sensing, EV, AV,
hmm
plane stuff. I imagine it's the same sort of concept. It's just how does the chirp pulse frequency change?
Correct. Yeah, absolutely. So we send out a frequency modulated pulse, and then we measure the return and a lot of signal processing to determine, because you may want to know if a user is approaching or say moving vertically or horizontally, I guess, across the field of view. And by Doppler and other processing, we can then we can you can configure the device for different wake up functions, right? To wake up the system depending on what you're trying to achieve.
Interesting. So a lot of the applications I would think about, like my less trained mind would go to like cameras sensing for a lot of these things, but radar checks the box in so many areas. How would you compare like an optical, camera sensor to a radar sensor? When would you start to think about maybe switching from either camera to radar or radar to camera?
Yeah, so I mean, there are other technologies out there. If you think about camera vision, which you're bringing up, cameras can almost, if you think about it, if you have enough processing horsepower and battery power, you can throw a lot at a camera, right? And get a lot of good information out of it. But, cameras aren't welcome everywhere, right? People don't want for privacy concerns and things like that, right? Also, the cost is going to go up. If you need more power, you need more processing. Now your whole BOM cost goes up. So depending on what you're trying to achieve, a camera may be needed, may not be, and we can provide, with a radar, the privacy, the lower power, the lower cost. And you also, the other thing to point out is a camera needs a view to the world, right? Radar can be completely concealed in the product enclosure because we can transmit through any non-conductive material. So now you're in a sealed environment behind your industrial design. Other competing technologies, we talked about this earlier, was ultrasound. Ultrasound has, it's got a limited range and a limited field of view. It can work in great environments, but it does have a limitation because you are sending acoustics out in the environment. And then again, like camera, it needs access to the environment. So it has to be able to transmit in the environment, but be protected from it at the same time.
That makes sense. The concealing sort of concept seems very important for industrial applications for sure,
Mhm.
or high stress environments. So how big is this chip? It sounds like there's a lot going on with it. What are kind of the dimensions of it?
Yeah, so with our latest and greatest product, with the antennas in the package, the package footprint is 6.05 by 4.3 millimeters by zero point 0.9 millimeters tall. So it's a pretty compact device with all the silicon, with the antennas integrated into it. Really, really good for a lot of space constrained applications.
Yeah, that's tiny. I'm looking at like my fingernail and trying to do
Yep.
the dimensions there. What other sort of technological advances or technology blocks do you have going on inside of this? We talked TXRX a little bit, but there's a lot that goes into making a radar actually functional and work. Can you talk me through that technology flow?
Yeah, so on the receiving end of the chip, there's an RF front end, and basically it's multiplex for transmit and receive. We also have some very sophisticated mixed signal and processing chain after the RF front end. So we can basically take all that data in. There's a variety of component blocks, and they're kind of standard processing. Some of them are pretty advanced. To then take that radar information and process that into the Doppler information, the angle information, the presence information as well. And then we also have to bring the antennas in and account for all that.
Definitely a lot of technology going into this. I feel like I have a pretty good understanding now of a bit of who's using these and how they work. Where is this technology going? What is next for radar, and what gets you excited about, a week from now, a year from now, and maybe a decade from now?
Yeah, I mean, if you look at our portfolio, we've released several generations of radar chips, and up to this point, they've all been on a bi-CMOS process. So what we're doing now is bringing to market a 60 gigahertz radar device on a pure CMOS process. And move into CMOS gives us some unique benefits that will enable a lot of capabilities in the market. The first one being much more higher transmit efficiency. So we'll be able to transmit longer range over wider field of view and do so at a lower power because it's a pure CMOS process. So, all these battery powered devices, this will be great for that as well. Because it's CMOS, we're able to integrate much more on-chip processing. So you'll be able to run this device autonomously and then wake on motion, say, without ever having to turn anything else on. We'll do all the we'll do all the sensing and then flag it to decide what you want to do in your system. So you can leave everything else off, further reducing power while the system's idle. That's a new capability. You weren't able to do that previously.
Can you explain the difference between bi-CMOS and like pure CMOS?
Yeah, by CMOS, so you have you have bipolars and you have pure CMOS kind of coupled together into your process. The bipolar devices kind of limit your integration capabilities, the size of your process. when you move to a pure CMOS process, you can really shrink those nodes down. So you can increase the processing capability, you can shrink your die size, and therefore your packaging size and power, and everything else scales with it. As you shrink, everything scales.
So you're talking about, giving the designer the ability to, say, hey, we saw some movement. What do you want to do? Can you tell me a little more about kind of what other sorts of capabilities you're developing there?
Yeah, so on chip, we'll be able to run software now because we're on CMOS. We can run on chip. You can power everything else down, and basically, depending on how you configure the device, you could say, okay, I detect a user in a given range in a given field of view, and basically determine now do I send a flag to the MCU in the system to then turn on and do other processing and turn on other hardware that you want to keep power down to save batteries. Um, so we can do a lot of that on chip now. And then let's say you do turn on. Now we're still collecting data with the radar. We're still collecting information. Now you may want to turn on other processors to do additional computing to maybe do classifications or other processing that you want to do in your system. Depends on the use case.
So what sort of systems are these getting integrated into? Who is saying, hey, I want the ability to, this may be too generic, but make my battery last longer or have that capability? Has there been any industries that are really driving that?
Yeah, I mean, a lot of home IoT applications, right? We talked about the security cameras, the doorbells. A lot of those are battery powered. And then you get into, say, smart thermostats. Sometimes those run on batteries, some don't. There's a variety of like battery power, you can think about like range finders and other things, handheld devices that goes into. And then it's just overall efficiency of systems, greener, call it capabilities of end products, and things like that.
Can you talk a little bit about how the rise of AI ML, both in the engineering world, which I think happened a little sooner in engineering than it did in kind of pop culture, how has that impacted how you think about your roadmap for future sensor design?
Yeah, I mean, if you think about with sensors, right, there's this concept of physical AI, right? So you're sensing in the physical world. Now, what do I do with this information and bring it to the AI? So we are seeing, this with more sensors and more data, you're able to fine tune these machine learning models and do more complex AI on them, right? So we are seeing trends of more sensors, but not only higher quality sensors, right? You're going to need cleaner data to generate these models, and also once the system's deployed into the environment, collecting that data and running them through the model and getting the correct output. So it is impacting our roadmaps for sure. We're taking these things into account and working with customers to understand where they're heading with their machine learning and with the future of AI as well. How do they plan to plug into that? It's going to definitely affect a lot of these sensors moving forward.
What advice do you have for engineers who are looking to integrate new sensors, maybe radar for the first time, or adding on to their suite of sensors to kind of build out the robustness of their system? What tips and tricks do you have for folks who are looking at that?
Yeah, I mean, we work with lots of customers, and what I think is really important when you're starting a new product endeavor using radar is working with your product team to make sure the requirements are well understood, because radar is going to collect a lot of information. It's very configurable. So understanding what those requirements are, and I'll kind of list a few, it's over what distance field of view do you want, because you can configure the device. What is the false positive rates you're looking at? How much power consumption? All of these knobs kind of work against each other, so they have to be kind of fine-tuned. So it's really having that set of requirements and set of use cases that the end equipment must meet ahead of time, so that then when you come to suppliers such as ourselves, we're able to support you in the best possible way to configure and work with you to actually get you to market as fast as possible. There's a lot of knobs to turn in these chips. We talked about the different blocks and the processing on the chip. Each one of those is there to support a use case. So we want to make sure up front we don't keep circling ourselves.
So really understanding your specific design parameters, what you're trying to do, and what sort of environment you're working in. The more you understand that, the more successful you can be integrating this into your systems.
Yeah, what are those boundary conditions so we can really zero in on the use case and make sure that we're getting you to market as fast as possible.
We're running towards the end of our time. We like to ask some kind of rapid fire questions at the end. If you had to think back throughout your career, did you have a favorite project or moment that you look back on fondly?
Yeah, actually, as we were talking, I thought about I brought up the 911 and using pressure sensors for floor detection. So, that was one project I worked on. A few years ago, there was legislation that 911, when you call, say, from a cell phone, it transmits your GPS information. But they then had new legislation that they wanted to determine what floor you're on and provide that to first responders. So the barometric pressure sensor is one such device that could be used because it's already in your phone and it can measure pressure. But it presents some unique challenges in that there's weather variations, there's different variable pressure throughout a building, let's say. So it's hard to turn a pressure reading into a floor number. So, we had to work with a number of other companies, third parties, as well as our pressure sensing knowledge, and come up with algorithms, as well as we did a lot of sensor fusion of using other sensors to then come up with an algorithm with all that sensor data to actually turn the data into a floor number. So it was really rewarding because it was kind of it was a tough problem to solve, but it also will directly impact society and it's going to save lives.
Yeah, I am an avid mountain biker, and I have a barometric pressure sensor on my watch, and I kind of chuckle when I look at the readings
Yeah.
sometimes because I ride enough to know like what elevation I'm at. So I imagine that was a very difficult challenge to get it locked into 10 or 15 foot difference between floors.
Yeah, depending on where you are in the world and you're mountain biking, the weather variation throughout the day could really throw that off. So that's why you can't just take one piece of data. You got to fuse it with other sensors in there and algorithms to work that out.
Has there been a technology development or kind of a turn that the world of technology has taken that has surprised you the most and maybe delighted you the most?
That's hard to pin down to one thing, but I was just thinking about this the other day. It's like one obvious one to me is, smartphones becoming supercomputers, right? I mean, I think the overall computing power and information that is packed into the palm of my hand in a smartphone is just truly amazing. I mean, it's like if you think about just years ago, the power of the processing power in a desktop, it had line power, it was fan cooled, and now that is in my pocket, in my hand. It's running on a battery. That to me is truly amazing. And if you think about the semiconductor industry, a lot of it has to do with that. I mean, it's the industry just keeps innovating, keep pushing the ball forward, continuous improvement and breakthroughs that have led to this. It's just one such example where all that semiconductor work has come together.
So, as some parting advice, as a last question, what advice do you have for people who are engineers who are early or mid career and looking to stay relevant and stay on top of their game for the future?
I think right now there's a lot of angst and uncertainty about how generative AI will change the course of history, right? One thing that kind of keeps me grounded is, over the course of history, we've seen a lot of technological breakthroughs that change either the course of history, they change our economy, they change the jobs available to us. So, one thing that keeps me grounded is kind of just this belief that, at each one of these new technology breakthroughs, it's important to not fear them and run for them, but to understand how these innovations can augment your own skills, they can further improve your productivity, and therefore the results you can deliver. So, as we think about generative AI and how we're going to use it and be more productive at work, my advice is kind of like use it to your advantage. What can you learn from it? How do you make AI work with you to thrive? We should use it for us, not against. It's not here to be worked against us. As an engineer, you could say, think about how to use AI to co-design systems with others, right? How to code software, how to augment your own skills, focus more on systems, stay creative. Those are kind of things I'm thinking about with AI.
Well, this was really incredible. Thank you so much for your time.
Thank you. Thanks for having me. Really appreciate it.
That was Ted Karlin, Senior Director of Marketing and Applications at Infineon Technologies. And this keynote was brought to you by Mouser Electronics. Delivering the newest electronic components for design, Mouser is your global authorized distributor for millions of components from over 1,200 leading manufacturer brands. Jumpstart your designs at Mouser.com. The All About Circuits Summit series happens each Wednesday in October, and all sessions from earlier this month are available on demand. Today's live sessions are all about sensors and cover topics like MEMS microphones, pressure sensing, and sensing for autonomous mobile robots. Each session you sign up for also gives you entry into the giveaway. And make sure to check out the microsites from our presenters to learn more about their topics. Thank you for joining me for today's keynote. I'm your host, Daniel Bogdanoff. I hope you have a great time in today's sessions, and I'll see you next time.